All right. Hi, everyone. We'll get started in a minute. You can put what answers you got for the first question in the chat. Okay, good. 23 is correct. Let's see. Ishan, do you want to explain?
So it says 40 more games. So you just add 40 to 50, which is 90, and 70% of 90 is 63. And you just have to do 63 minus 40 to get 23.
Okay, good. So we know that the team won 40 out of the first 50 games. And there's a total of 90, including the remaining 40 games. So if they won 70% of the total, 70% of 90 is 63. So if they won 63 total, if they won 40 of the first 50, that leaves 23 to be won in the remaining games. So we know there's a total of 90 games because 50 games were done initially, remaining 40 games. So out of the 90 games, 70% is 63. They won 40 of the first 50 games, so that leaves 23 left. Any questions on this? Okay, let's go to the second one. Okay, 138 is correct. Nidhi or Neil, can you explain?
Yeah, so I just split it up into categories and then added them together. So for twos, the entire category from 200 to 299, that's 100 numbers. They all contain two. Going down to the tens place, I'm not counting 20 here, so I'm just doing yeah, so it would be 10 and then 10 per 100. So that's the 100 and the 300 category, which means that's 20 numbers for that place. And then for 21, 20, 22, 23, 24 to 29, that's 8 numbers times 2 is, 9 numbers times 2 is 18. And then 100 plus 20 plus 18 is 138.
Okay, good. Let's include that. Okay, so the first set of numbers we can kind of easily see is, okay, if I start the number with 2, it has the digit 2. So I can take out 200 to 299 gives me 100 numbers, right? So that's the first category. Now let's think about 2 being in the tens digit. That could be 120 to 129, 320 to 329. So there's 20 numbers with 2 in the tens digit. And now 2 in the ones digit. So that could be 102, 112. But we have to be careful here. So we can take 122, 132 up to 192. But we have to be careful of this 122, right? This is being counted 2 times because it would be counted in 120 to 129 as well. So either we can take that out. So there would be these 8 numbers. These 9 numbers. As well as the same thing with 302, 312, 322. 322 again has the same problem, so we could skip that. 332, 342, up to 392. So the same thing would be 9 numbers. If we add these up, we get 100 plus 20 plus 9 plus 9 is 138. Okay, good. So this is the kind of main way of doing it. This is also related to one kind of previous technique we've seen before. Anyone remember the name? So it's related to, in this case, there's two things that overlap here, right? So we could have done this in a different, yeah, go ahead.
Was it the bars and stars one or bars and something?
So that was for like the counting when we want
Oh.
to count different kind of
Yes.
ways of grouping.
Sorry, never mind.
No problem. Okay, so so if we think about this, there's another way of counting this, right? So instead of counting, we removed the overlap in this way. Instead, we could have said, okay, let's count all the ones where twos are in the tens digit. So we know there's 20 of those, not including the 200s. We can count all the ones where twos are in the units digit. And we can subtract the ones which are overlapping, right? Twos are in both the tens and units digits. So instead of counting this as 20 plus 9 plus 9, if we had done it this way, how many numbers are there where twos are in the tens digits? So that's 120 to 129 is 10 numbers, 320 to 329 is 10 numbers. So that's 20 plus twos are in the units digit. So that's 102 to 192, 10 numbers. 302 to 392 is 10 numbers. So that's another 20. And subtract the two numbers which are overlapping. So which are 122 and 322. So that would give us the same 40 minus 2 is 38 to add to the 100. But in this way, when we're kind of adding it twice and then subtracting, anyone know the name of this? So this is the principle of inclusion and exclusion. I think we saw this with a few problems before. But the idea is it's not exactly needed here because we can also just think about kind of, we know there's an overlap here and we exclude it when we are thinking about 102 to 192. We don't want to count 122 twice. Or you could say, let's explicitly count it twice. Let's count the tens digit independently. Let's count the units digit independently. And then think about how many are in the overlap and subtract that out. So it seems simple here, but this extends to the advantage of this idea is we can extend it to 3 categories or 4 categories and use the same technique there. Any questions on this? Okay, let's go to the last one. Okay, good. 180 is correct. Ishan, can you explain?
Yeah, I just went up by increments of 60. So I just found like the prime factorization in each one. So for 60, it's a 2 to the second power times 3 times 5, which means it has 12 divisors. For 120, it would be 2. I'm pretty sure it would be. Sorry.
No problem.
Would it be 5 times 3 times 2 to the third,
Okay.
which would be 12 divisors. And there and so in total you have to find 18 divisors. So and then for 180, it was 3 to the second, 2 to the second, and then 5, which gives you 18 divisors. So then I just listed all the divisors and then counted to see if there was 6 even and 12 odd, 6 odd and 12 even. And then I got I got 1, 2, 3, 4, 5, 6, 9, 10, 12, 15, 18, 20, 30, 36, 45, 60, 90, and 180. And six of those are odd and 12 of those are even. So yeah, that's the answer.
Okay, that's good. So that is correct. So how did you come up with 60 as like the number you started checking?
Because it has a lot of it has most of the first 10 divisors. So I just assumed, I wasn't like fully sure. I just assumed that it went up by every 60.
Okay, good. So yeah, this is one approach. So I think you did get a little bit lucky that 60 worked and it was the divisor of that. And then yes, so 180 is the smallest value. But let's look at a different way of doing this, which will also kind of confirm that in this case, we might not be 100% sure that there is nothing smaller than 180 that also has 6 odd and 12 even, right? So here we can be sure if we list out the divisors of 180, as Ishan did here, we can count, okay, there are actually 6 even, 6 odd divisors in this list. There are 12 even divisors in this list, and we can confirm this. But how do we know maybe 116 or some smaller number than 180 also doesn't have this? So let's try to find a different way of approaching this. And to do that, let's start off with, I think implicitly this is used or in kind of computing this, but how do we find the number of divisors for a given number? What's the technique to do this? A formula or technique?
Prime factorization.
Okay, and then what? So let's take a number like 60 is 2 to the power 2 times 3 times 5. 3 to the power 1 times 5 to the power 1. Okay, so we have the prime factorization. What next?
You multiply them together.
Close. Yeah, you multiply them, but we have to do something before that.
I'm not sure.
Okay. So we know it's 2 to the power 2 times 3 to the power 1 times 5 to the power 1. In this case, how many divisors does 60 have? Okay, so the trick is actually you can take each exponent. So in this case, it's 2 to the power 2 and add 1 to it. And 3's exponent is 1, add 1 to it. And 5's exponent is 1, let's add 1 to it. And multiply these together. So what do you get here?
12.
12. Okay. So can we confirm that 60 actually has 12 divisors? What are its divisors?
Two, 4, 3, 5, 1. I'm at 6. 9, 10. Wait. Yeah. 12.
Mm-hmm.
20.
15, good.
20.
30.
Mm-hmm.
60.
Okay, and how many things are on this list now?
12.
Good. Okay, so this matches up, right? So this trick seems to work here. So what we do, the trick is basically, so this is our first step. We haven't gone to the original problem. If I have any number and I want to find the number of divisors it has, I can take its prime factorization, look at each exponent here. Take each exponent, add 1 to it. So 2 plus 1 is 3, 1 plus 1 is 2, 1 plus 1 is 2, multiply them together. 3 times 2 times 2 is 12. And it worked for 60, right? So we listed out 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, 60 are all the factors of 60. Okay, any ideas why this works? And that's going to help us with this problem with odd and even. So what is true about the prime factorization of any of these divisors? Do I know what the prime factors of any of these will be as well?
It would comprise of either 2, 3, or 5, all of them.
Good. So we know it cannot have some other prime factor, right? If it had a factor like 11 or 13, then it can't be a divisor of 60, right?
Yes.
Okay. So now we know that each of these divisors can be written as, or as a prime factorization as 2 to the power something times 3 to the power something times 5 to the power something. Does that make sense to everyone? So any divisor of 60 must be in this form. Okay. What are the choices for this a? The exponent of 2.
It would be either 1 or 2.
Close. Anything else?
0?
0, right? So it could just be not a multiple of 2, right? Let's look at 3, for example. What is the prime factorization of 3?
1 and 3.
Yeah, so 3 to the power 1 multiplied by, there's still a number here, it's just 2 to the power 0, right? There's no 2's, and 5 to the power 0. So a can be 0, 1, or 2. So what does that match up to in that product that we have?
Oh, so we're starting with 2 to the power of 2. So can you grab the transfer? Sorry. So the 2 is accounting for what we have, and then the 1 that we're adding accounts for the 0 that's not visible right then.
Good. Yeah. So we know that 60 has 2 2's in its prime factorization, right? So we know that any divisor of it will have an exponent of 2 being either 1 or 2 or 0. So that's why we add 2 plus 1 here. So that essentially this number is the number of choices for a here. So that's 0, 1, or 2 could be the exponent of a. Okay, now let's do the same thing for b. What are the options for b?
0 and 1.
Good. So that corresponds to this 1 plus 1, which is 2. Let's do the same thing for 5 and c here. What are the choices for c? So it's the same thing as b, right? Again, 5 to the power 1. So this can be 0 or 1. So this is 1 plus 1 is the number of choices for c. So the total is 3 times 2 times 2, which is 12. But essentially, each divisor is just a choice of a, b, and c. So if I think about when I know that there's some number of odd divisors and some number of even divisors, could I actually use this approach to count the number of even divisors of 60 instead of the total number of divisors of 60? What kind of constraint does that add? So there's one particular value of a, b, or c that will lead to it not being even. Which choice is that? So if I set a to be 0, it would definitely be odd, right? There would be no factor of 2. So even divisors of 60 require a to be greater than 0, or a is equal to 1, or a is equal to 2. So what this means is that the number of divisors of 60 that are even are, instead of doing 2 plus 1, we just do 2 because it's a is 1 or 2 times the exponent for 3 or b could still be 1 plus 1. It could be 0 or 1. The exponent for 5 could still be 1 plus 1. So it's 2 times 2 times 2, which is 8. So there's 8 even divisors. And we can double check that here, 2, 4, 6, 10, 12, 20, 30, 60. And the remaining are when A is 0. So that's only one case times 2 times 2. So there's 4 odd divisors. So this is nice because now we essentially kind of have a formula for finding the number of odd divisors of a number and the number of even divisors of the number. So if we want all the divisors, we add 1 to each exponent and multiply them. We want only the even divisors. We still do the same thing, but don't add 1 to the exponent of 2 and add 1 to the other exponents and multiply them. And for odd divisors, we add 1 to all exponents other than 2 and multiply them. Okay, so now let's go back to the original question. So we want the smallest positive integer with 6 odd divisors and 12 even divisors. So if we think about it, so the even divisors is twice the number of odd divisors, right? So that means that the exponent of 2, so we know that the exponent of 2 is the multiplier, right? Between the odd and even, what we did here, in one case, we just did 1 times 2 times 2. And in the other one, we did 2 times 2 times 2. Because the exponent a and 2 on the original number was 2 itself. So in the even one, it could be 1 or 2. In the odd one, it had to be 0. In this case, again, we see that 12 is double of 6. So that means that we know the number must have 2 to the power 2 in its prime factorization. So that part is fixed. Now we know that the remaining part of the number, whatever the prime factors are, there must be 6 divisors. So there's 6 odd integer divisors, and that's essentially just looking at all the divisors, not including this power of 2. So if we think about it, whatever kind of, it's 3 to the power something times 5 to the power something, or 3 to the power something times 7 to the power something, we know that if I take the exponents of each of those, add 1 and multiply them, I should get 6. So if I need to get 6, I know that must be in the form, so I'm adding 1 to each divisor, so it should be in the form 2 plus 1 times 1 plus 1. So this tells me that this number must be in the form some prime factor a to the power 2 times some prime factor b to the power 1. What are the smallest possible values I can choose here for a and b? So I know it can't be 2, so a and b are prime numbers, but not 2, because I'm only looking at the odd part now.
A could be 1 and B could be 6.
So we want to make sure a and b are prime, right? So
A could be 1 and B could be 3.
Okay, 3 is good. So 1 isn't actually prime. We need something bigger than that. So what's the next prime number?
5.
Good. Okay, so the smallest values I could choose here are 3 and 5. Now to make this as small as possible, do I want to make A3 or A5?
3.
3, good. Okay, so the odd portion will be 3 squared times 5. So this is 45. And we already said that because we saw that it's 12 even divisors and 6 odd divisors, we know that the powers of 2, there's 2 kind of factors of 2. Because when we saw this here, it would be a times the number of odd divisors is the number of even divisors. So we can multiply this. So this is the smallest kind of odd number that has 6 divisors. Multiply this by 4, and we get 180. So this way kind of confirms that we can't actually do anything better than 180. 180 is the best we can do. And now we also have this nice formula to say if I have any number, I know I can take the prime factorization. If I add 1 to each exponent and multiply them, that's the total number of divisors. If I take the power of 2, whatever that power of 2 is, and don't add 1 to it, and multiply with the rest of them, adding 1, that's the number of even divisors. The number of odd divisors is you force the power of 2 to be 0. So that means you just ignore the power of 2 completely and just add 1s to the remaining ones and multiply them. And that gives me the odd divisors. Using this, I can backtrack to say, I know 12 is the even divisor, 6 is the odd divisors. So based on this way of computing this, the exponent of 2 must be 2. And then the odd portion, I know there's 6 divisors. The smallest odd number with 6 divisors must be 45 because I need something squared times another prime number. So that must be 3 squared times 5, where these are still odd. So that's 45 times 4 is 180. So now we're sure that 180 is the smallest number. And like Ishan did, we can kind of also list the divisors of 180 and confirm that there are 6 odd divisors and 12 even divisors. Any questions on this? Okay, that's it for today's class then. We'll see you all next week.
Thank you for
Thank
the
you.
class. Bye.
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 Thank you.